Bismillahirrahmanirrahim. Assalamu alaikum. So in the previous lecture we had discussed the so-called planar, linear and autonomous systems. We had defined these and we had seen that a typical planar linear autonomous system looks like time derivative of capital X of t to be a times x of t, where a was matrix 2 by 2 matrix and this was vector, uh, 2 by 1 vector, and this was 2 by 1 vector, and more precisely x of t was x comma y, where x and y were the functions of time, and a was a matrix in general, could look like this. Well, this side shouldn't depend on time, so like you can write x prime to be ax, because this x, these these this vector x of t mean x as a function of t and y as a function of t. So I'll be writing this, and because this system is autonomous, so this side will not depend on time explicitly, and the system would be looking like this: x prime to be ax plus by and y prime to be cx plus dy. So next thing that I want to make clear for all of you is we want to see that what do we mean by the solution of, or in other words, how the solution looks like for such systems. So we want to see that. For that, for the motivation, we will take an example and we will see what is the meaning of how the solution looks like. I'll consider this example where x prime is x and y prime is 2y. So this can be written as x prime y prime to be 1 0 0 2, and this is my x and this is my y. So this is a, this is x, and this is x prime. So this is an example of autonomous planar linear system. I want to solve this. I'll solve this first and then I'll let you know what do we mean, how does the solution behave graphically. So let's solve this equation 1. There are too many methods to solve this, but for the moment let's solve this. X prime is x, so this implies 1 over x dx is dt. By separating the variables, this is natural log of x, which is t plus some constant c. On the same lines, we can, or we can also write this x to be a e to the t. On the same lines, we can solve this 2. This is from 1, and from 2 y prime is 2y, or I can write 2y, or maybe y dy to be 2 dt. And then again, by separating the variables and integrating, I get natural log of y to be 2t plus some constant, let me call this c1, and then definitely my y of t is going to be a e to the, this was a1, let's say, and this is a2 2t. So let's call this equation 3 and let me call this 4. Now what I have got is x of t to be a e to the t a1t and y to be a2 e to the 2t. Let's assume that x of 0 is, let's say, x naught, and y sub 0 is y naught. In other words, the initial condition for the system is x naught y naught. So if we apply this initial condition over here, we can write x of t to be x naught times e to the t, and y of t to be y naught e to the 2t. But I can take the value of t from this equation and put it over here. So from here my t is going to be natural log of x over x naught. So if I insert this value over here, then my y of t is going to be y naught e to the 2 times natural log of x over x naught. So now I have got to tell you in two ways. One way is, so this was a solution for the system. This was the solution for the system. Let me put them in a more better way. X of t to be x naught e to the t, and y of t to be y naught e to the 2t. Or I can write this as x naught e to the t and y naught e to the 2t, or maybe x naught e to the t and y naught e to the 2t. This was the solution of my system. You can realize that this is parametric equation of a curve and R2. This is nothing but the parametric equation of a certain curve in R2. And if you are varying this x naught and y naught, in other words, if you are varying the initial condition, you will be getting different curves. Okay, but we also know that if we are given with parametric curves, then we can try to obtain the curve y in terms of x or in terms of x and y. So for that we had to take the value of t from one equation and had to put into other, or we have to eliminate t from both of these equations. And we already have seen that this gives me y of t to be y naught e to the 2 times natural log of x over x naught. So this is going to be the curve which times t also. This is going to be the curve that is the solution of my this system. X prime to be x and y prime to be 2y. As the x naught and y naught will be varying, there will be different curves depending on the x naught and y naught. We can plot these on Desmos. So here are the equations. So here is the equation, here is the solution that we had for the system. Now let's vary these x naught and y naught. So let me allow these x naught and y naught to vary. So now you can realize that x naught and y naught, as x naught and y naught are varying, we are getting different curves. So for each initial condition we have a different curve in R2. So you can realize that. Okay, let me stop and explain one more thing. Okay, so let's come back to where we were discussing. You know what? The curve that we had was equal to this: x naught e to the t and y naught e to the 2t. But if I calculate its time derivative, x primes of t, then we know from our basic calculus to our vector calculus that this x prime is going to be at every t, this vector field is going to be tangent to x. So this x prime is tangent to x. What does this mean? That if you are unable to plot x of t, rather you can plot these tangent vectors, and from there you can get the idea. For example, for a certain initial condition we had this curve. So this means that my tangent field should also be looking like this. And we also know that for a certain initial condition we had this behavior also. So my tangent vectors should look like these also. And for a certain initial condition we had this behavior too. So that means that so for example there was like this as well, because when we were changing the x naught y naught we were getting different curves this way, if I'm not wrong. So in order to plot this x of t, we can get the idea of x of t from these vectors, how these vectors are behaving. So instead of plotting the x of t, we will usually be plotting the x prime of t, in other words x prime instead of x, which will be giving me tangent vectors for this, and from where we can conclude that how the curve would look like. And this plotting of this x prime into plane is called making the phase portrait. So for this system that we had 1002 xy previously that we discussed, our phase portrait would look like this, something like this. We gonna see. But there are online phase portrait plotters as well. I've got one, and let's go to that and see. So let's see how the phase portrait looks like, or how the tangent field look like, or some people called it direction field. So let's see that how these tangent vectors for the x of t look like, or how the phase portrait look like. So our equation was x prime to be x, and this was 2 times y. Don't forget to put this steric multiplication. So let's plot this. So aha, that's cool. This is the plot. This is the plot. Now this plot is showing me that these are the tangent vectors. There will be different curves, and for every curve there will be tangent vectors, and these are the tangent. If you will click over here, you will get one curve. So this is the curve where these vectors are tangent. This is the curve, this is the curve. So this is the curve. Now this is the curve. So this is the curve, this is a curve. Again this and this and this and this. So now you can see that uh, despite instead of plotting these curves for different initial conditions, you can draw a phase portrait, and from that phase portrait you can have the idea of how your curves will look like for different initial conditions. So, and in fact the fixed points will be playing a key role. So you can see that here 0 comma 0 is a fixed point, and you can also see that flow is outward. This 0 0 is going to be the fixed point we will see later, and you can also see that flow or the direction field or the flow is outward from the 0 0. 0 0 is unstable point. We will see later on, so this was an informal way of telling you how the solution to a two-dimensional or the planar linear autonomous system will look like. So we'll be coming in the next videos where we will be analyzing more these planar linear autonomous systems. Till that, then, thank you.